All right, today we're going to take a look at section 11.3, which is the dot product. So this is one method for multiplication, if you will, of vectors. There's two methods we're going to discuss. The dot product is the first one. Next time, we're going to look at 11.4, and that's the cross product. So it's a different kind of a product. So the dot product is our first one. So the dot product of two vectors, u and v, is the component-wise multiplication the multiplication of each of their components, and then the sum of those values. So u1, v1 plus u2, v2. And three-dimensionally, just like we saw everything going on in 11.2, just extends to being the u3, v3 at the end, addition to. Okay, so notice, you multiply two vectors here, and what do you get? A number. You get a scalar. Okay? So with the dot product, you always get a scalar or a number at the end. Okay? Some properties of the dot product. And they all come very directly. Like, we could legit prove all of these things. They're not very difficult because we could write them down from that definition. Every single one of these would work just fine. So the first one is that we have commutativity. So u dot v is the same as v dot u. We have a distributive property. So u dot v plus w is u dot v plus u dot w. We have sort of an interesting associative property. Looks a little bit different than what you're used to. You could actually take the scalar c, and you can multiply it by the dot product. And it would be the same thing as multiplying it by either of the individual vectors first and then doing the dot product. I have a piece missing on number 4. I think I knew that too, and I never went back and fixed it. When you have the 0 vector times the vector v, you end up getting the 0 as the scalar multiple, or the scalar value. There's type 1, the last one too. All right, and then v dot v is the magnitude of v squared. 2 typos on there. Could be worse. Okay, you guys ready to try some? Yeah? Okay. So this is going to feel like arithmetic class a little bit with some vector notation thrown in. So we are going to find, I think it's 5 different quantities listed there above, for the vectors u, which is 2, negative 1, 3, and v, which is 0, 2, negative 4. So the first part A, is wanting us to find u dot v. So we're going to multiply component-wise, I didn't mean to put that there, and add. So we have 2 times 0 plus negative 1 times 2 plus 3 times negative 4. We're going to multiply, we're going to add, subtract, and what will we get?
Negative 14.
Negative 14 is right. Okay, let's do the second one. So B wants us to find the dot product of u and itself. Okay, so we actually just have the square of each of the terms because it's just u with itself. So it's 2 times 2 or 2 squared. It's negative 1 times negative 1 or negative 1 squared. And then it's 3 times 3 or 3 squared.
14.
That one's 14. I promise not all answers are 14. The third one is the magnitude of u squared. So that's the 14. It's the same thing we did in the line above, right? Just different notation for it. Good. D is the vector u dot the vector v times the vector v. So that looks a little funny. You notice there's not a dot after the parentheses. We know what u dot v is. What is u dot v?
Negative 14.
Negative 14, we did it above. So it's negative 14, and then it's times the vector v, because it's now a scalar, right, times v, and scalar multiples just multiply each of the components. So we multiply each of the components of v. So we have 0, negative 28, and 56. Does it make sense to everyone? Okay. So, oh, last one, and then I'm going to make a comment. E. U time a dot 2v. So you're welcome to do it as is, right? To take the vector u and then find the new vector that's in the parentheses by multiplying each component. Or, if you wish, you can pull the 2 to the front. So you can shift the 2 around, and it might be helpful. In fact, I think it'd be friendly to do that on this one because we've already done u dot v, right? It was negative 14. So we might as well make use of the piece of information we've already done, and we'll get negative 28. Okay, so what I was going to say is that unlike algebra, it now matters whether you actually have the dot or you don't have the dot, right? Think about when you're working with algebra and you're first learning not to use x's for multiplication. We talk about using parentheses to show the multiplication. We talk about using dots between them to show the multiplication. And it didn't really matter which one you use. You can use either. Here, you need to be careful because they do mean something different now. Okay? All right. Angles. So between two non-zero vectors, there will be an angle measure. Theta is the angle, and it is found by the cosine of theta is actually the dot product of u with v divided by the magnitude of u times the magnitude of v. And that's awfully tiny. Sorry, it's so small on that one. So we're going to find some angles between something next. So we're going to be given a vector u and a vector v, and we're going to apply this formula. So the first thing I'm going to do is I'm going to rewrite this formula on this page just so we have it written down. Cosine of theta is u dot v, which is the magnitude of u times the magnitude of v, like that, and they're multiplied values. All right, so u dot v will be first. So I have 1 times 2 plus 3 times 0 plus negative 2 times negative 3. What does that give us? 8. Is that okay for everybody? All right, I also need to find the magnitude of u, and in a moment the magnitude of v. So the magnitude of u, and it's not the magnitude of u squared here, it's the magnitude of u, which means it has the square root on it, right, from before. So we need each of the u values squared. So we have 1 squared, 3 squared, and negative 2 squared. Yeah. Apparently when I was making this lesson, 14 was a favorite number. I don't know. And we're going to do v. So same process. So we have 2 squared, 0 squared, and negative 3 squared. This one's not square root of 14. This is square root of 13, yeah.
Close but not quite.
Close but not quite. Okay, all good? Okay, so we're going to go to doing the cosine of theta is equal to the u dot v, that was the negative 14, over the square root of 14 times the square root of 13.
Should that negative 14 mean 8?
Sorry, yes. I wanted to have 14s everywhere. Thank you. Let's do an 8 there. That'd be better. All right, trig, how do you solve for this theta?
Inverse cosine?
Inverse cosine, and in fact, that's really good because our calculator will do that for us, right? Because that's an ugly value on the other side. So we don't have to unit circle or anything like that. So we're gonna do the inverse cosine. Feel free if you would like to go ahead and simplify the denominator before then, just to make it a little bit easier for your calculator to deal with if you wish. It's a 132 in that denominator.
182.
Yes, if I could read my own writing. Thank you, 182. That is what I've written down. All right, what is the inverse cosine of 8 over the square root of 182? We'll go with 3 decimals.
53 point.
Let's do radians first. Part A asks for
Well, I
radians.
am in degrees.
936.
Okay, 0.936 for our radians. That was part A. So I'll put that as part A. Part B turns it into degrees, and so for degrees, if your calculator will do it real quick, then that's fine. If you wanted to do it by hand, you're just multiplying by 180 over pi. If you remember doing that from trig or not, but that's what you do. And what did you have, Adeline?
53.630.
Mm-hmm. Okay. So we have 2 vectors. There's an angle measure that's between them if we lined up their initial points, right? You can see the angle measure, and that angle measure would be about 54 degrees. Okay. Are you familiar with the word orthogonal?
Yep.
Okay. Some of you are yeses. Jill, is that a no? No. Okay. So my physics people are yeses, I'm guessing.
Familiar with what?
Familiar with the word orthogonal.
That was,
Is that a word you've seen before?
that's my calculator for me.
Okay, pre-calc. Okay.
I'm
Okay, if you're not, that's fine. That's why I wanted to ask. The word orthogonal means perpendicular, but it's used when we're talking about things in 3 dimensions. That's when you usually see it used. So right next to the word orthogonal, perpendicular. So we have 2 vectors, u and v, that are orthogonal or perpendicular when u dot v is 0. Okay? So u dot v on our last problem was 8. Right? They weren't orthogonal. And we verified that to some degree because we found the angle. Right? The angle was 54 degrees about. So if we're wanting to decide if something is orthogonal, it's equivalent to finding out if their angle is 90 degrees, but it's quicker than that. We simply need to find out if the dot product is 0. So I've got an example here, and it wants to know if it's orthogonal, so we do the dot product. And we'd have 2 times 2 plus negative 1 times 4. And we get 0. So yes, they are orthogonal. I could write orthogonal.
Won't it look like it was parallel?
That's actually what I was going to bring up next. So my
Okay.
notes and everything. Okay, so the directions say to decide if they're orthogonal or parallel or neither. So I chose it because I wanted you to see one that was orthogonal, obviously. But do you remember what we did earlier in section 11.1? How did we decide if things were parallel?
I think we multiply by like a scalar.
Yeah, if they were scalar multiples of each other. So these two would not be scalar multiples of each other, even if we had not done the orthogonal part. And it's an obvious one. What's obvious about it?
One number is the same as the others.
Yeah. One number, that's actually 2 things that are obvious. One number, so Robert says the 2's are the same, right? So clearly that's going to be a problem. And then some of you noticed the signs. One of them has a negative sign on -1, but not on the 4. It's not negative. So both of those are red flags for the fact that this is not parallel. But that's what we would be looking for is scalar multiples.
Dr. Hill,
Mhm.
I'm not exactly sure what orthogonal means.
Means perpendicular.
Oh.
That's what I was just saying before.
Sorry, I could get
We hear the word orthogonal used instead of perpendicular though, when we're talking about 3-dimensional objects. Perpendicular, think about in an XY plane. If you have a standard, XY plane like this, and you have a line, get a color going here, and you have a given point, there's only one perpendicular line at that point, correct? That's one of those Euclidean postulate kind of things. And those of you who haven't had geometry, I think that's in the spring. It's fun. You'll learn more about the Euclidean stuff there and non-Euclidean. The problem is that if you three-dimensionalize this, there's lots of perpendicular lines to that point because they come out of the page, if you will, right? So orthogonal is a broader description, whereas perpendicular is very specifically defined for 2 dimensions. But it's the same idea. It forms a right angle, a 90-degree angle. Okay, ready for the next thing? We're going to do projections. Okay, so we do projections all the time when we think about like a right triangle. So let's write this down, and then I'll give you a sort of a visual description of what's going on. So this is talking about what happens when we have projections. So U and V are non-zero vectors. U is the vector W1 plus W2, where W1 is parallel to W2, and W2 is orthogonal to V. W is called the projection of U onto V, or the vector component of U along V. It's denoted by W of 1 equals the projection of V along U. I said that wrong. Projection of U along V. That's the notation. W2 is simply U minus W1. And that is the vector component of U orthogonal to V. So we've done this already. You just didn't know that's what it was called. So as an example, think about having the vector in number 2, U. But let's just do it 2-dimensional so I can draw the picture better. It's I plus 3j. Okay? That's the vector, except not the z component. What does I plus 3j mean? Well, the I tells you that you have 1 in the I direction, right? So visually along your graph. Means you're going right 1. And the j tells you you're going up 3. So if you were to draw this vector, it would look something like, let me get this orange, like this, right? But if you were to project it, right, think about like a shadow that casts straight down onto the x-axis, you'd get the I component. That's the projection down onto the vector that's the one that we've got as horizontal. And if you're projecting over to the other axis, you'd have the j component. I and j are these components that this is talking about. But what this is telling you is that it doesn't have to be done in the xy plane where x and y are the projections, or the xyz where x, y, and z are the projections that you're making. You can do it anywhere. So you could, and my picture, I'm doing this off the cuff, so if my picture messes up, we'll fix it. So let's say that this is your vector and you're trying to project it onto another line. And the line is not the x, y, I didn't mean to do that. There we go. And you're trying to project it down here, right? It's at an angle. Well, you do the same thing. You would still go straight down at a perpendicular, right? It's going to be perpendicular down, like that. And then the parallel part that it's talking about is over here, and you'd be projecting it back over here. Good grief. Trying to get so many colors. That's not a good one. So this would be W1 down here, and this one would be W2 over here. Okay, my picture is not perfectly rectangular. It should be, and for this to be right. But you're projecting it onto somewhere else. Okay, we do this with projections all the time. You're just usually projecting it against something that's perpendicular already, right? Like even when we project in real life onto a screen, right? But have you ever tried to project to something where the wall is not straight or the surface is not straight, and how it sort of elongates and it makes things look weird? It's a projection as well. So here we're projecting it down and to the left onto a different kind of a surface. All right, so let's do one more theorem. If U and V are non-zero vectors, the projection of U onto the vector V is the projection of u onto v, is u dot v over the magnitude of v squared times the vector v.
What's square?
It's a typo because I didn't get it in here right. I'm reading off my paper, which is correct, and this is not. So I'm sorry. On the bottom here, it should say the magnitude of v squared. Thanks for catching that. I would have even glossed right past it because I wasn't reading the right screen, which is good. My notes are right. The screen's wrong. It's the magnitude of v squared, and then v on the outside. Okay, so we're going to do some projections. So part A, we're going to take the projection of u, find the projection of u, v, onto u, I didn't write this very well. Projection of u onto v. I think that I just wrote the v in the wrong place, is what I did in my notes. So projection of u, which is 2, negative 1, 3, onto v, which is 1, 2, 2. So it's the last theorem that we just did. I'll rewrite it up here as well. So this was the projection of u onto v. It's the dot product of u and v divided by the magnitude of v squared. And all of that is times the vector v. So we need u dot v. So let's do that first. So we have 2 times 1 plus negative 1 times 2 plus 3 times 2 for a grand total of 6 is right. Good. We need the magnitude of v squared, which really just means I need v times v. So I have 1 squared plus 2 squared plus 2 squared, which is what?
3.
We don't have the square root of it.
9.
Oh.
It should be
Oh,
9.
we use the squared, so.
Yep, the magnitude of v squared, so it should be 9. Yeah. Everybody good? Okay. And then the projection of u onto v is that value, 6 over 9, that we just got, times the vector v, which is 1, 2, 2. So 6 over 9 is
Thirds.
2/3. And then we're distributing it through the 1, 2, 2. So you'd have 2/3, 4/3, 4/3. So the 3 components of projection would be 2/3, 4/3, and 4/3. And then the vector component of u orthogonal to v. So if you take a look back up, that's finding the W2 component. I didn't label A and B. This is A. This is B. So W2 is, this is from the previous slide, U minus W1. So this one right here we found was W1. And so we have, going back and forth, U is 2, negative 1, 3. And we're going to subtract 2/3, 4/3, 4/3. Okay. 2 minus 2/3. 4/3. Negative 1 minus 4/3.
Negative 7/3.
Uh-huh. And then 3 minus 4/3.
9/3. 5/3.
5/3. Yep, 5/3. So this one would be W2.